Hello to all who have joined us so far. We're going to wait a few minutes to get started so that more people have the opportunity to join. Hello all and welcome to the UFS webinar. This webinar is hosted by the National Weather Service in the Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. I'm Shira and I'm here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present at this webinar in the future, you can email your recommendations to ufs.modeling@noaa.gov and we will take your suggestions into consideration. Due to the high number of attendees, you will be in listen-only mode during the event. You will not be able to unmute. If you do have any questions now or during the event, please submit them on the Google document that will be provided in the chat box shortly. Presentations last about 45 minutes, followed by a Q&A session for about 15 minutes. Please type your questions onto the Google document during the presentation. Today's webinar presentation is the Warn-On Forecast System, Probabilistic Prediction of Individual Thunderstorms. We're lucky to have the Division Chief of Forecast Research and Development at the National Severe Storms Laboratory with us today, and she's going to help me by introducing today's speaker, Patrick Burke.
Okay, it's my pleasure to do so. Hi everyone, I'm Pam Heinzelman, and Patrick learned just a little bit about him before he begins to speak. Patrick Burke worked as a National Weather Service forecaster, including 5 years as a lead forecaster at the Weather Prediction Center. In 2020, he brought his operational experience to the Warn on Forecast Research Group at the National Severe Storms Laboratory. And he is now the Warn on Forecast program lead. We're very pleased that he's here working with us and has made a big difference. He holds an MS in meteorology from the University of Oklahoma. And growing up in the severe weather culture of Oklahoma, he has always been motivated to help people stay safe during severe storm and flash flood events. In his spare time, Patrick enjoys running and writing music.
Awesome. Thank you, Pam. I'm not seeing the option to share my screen, so there we go. Yeah. Well, thank you, Pam, and I want to thank the organizers. This is such a great opportunity to speak to a wide audience about the Warn on Forecast system. And for the rest of the hour, I'll just call that WAFS, so you know what I'm talking about. But this is a really exciting experimental technology that has forecasters excited, has administrators excited when we talk to them. And whether you're an avid user of the experimental runs already, or if you have just vaguely heard of the Warn on Forecast concept, I've designed this talk to where everyone should be able to get something out of it. And since there's so much to talk about, let's just go ahead and dive right in. Okay, well, the Warn on Forecast system makes predictions of all kinds of weather, but one of the motivations has been to give forecasters tools that can help improve lead time, especially for tornado warnings. And if you look at the figure from Brooks and Correa here on the left-hand side, you'll see tornado warning lead time over the years has been relatively flat. There was an increase in the 90s with the deployment of the NexRad radar network, but otherwise it's been pretty flat or even falling in recent years. And one of the reasons for that is that we've hit kind of a natural limit for lead time if you're using primarily radar data and storm spotter reports to issue tornado warnings. And you can not have to imagine too hard to find some groups of people like those that live in mobile homes, those are outdoor events like sports events or concerts, who certainly need more than the average lead time, which is about 13 minutes for tornado warnings. So one of the difficulties here is that there's just not been a numerical weather prediction component to serve that kind of pre-warning time frame. And so back in 2009, the National Severe Storms Laboratory envisioned this grand kind of a moonshot project to develop a system of numerical weather prediction that's specifically tailored to that pre-warning kind of in between the watch and warning timeframe, 0 to 6 hour. And so you had storm scale models in the community that were getting better and better all the time. And NSSL set out to develop for those models very rapid data assimilation and rapid relaunch of new forecasts that could keep pace with the details of severe weather at the city level. Another way to think about that problem is to consider what happens between the issuance of, say, a tornado watch and a tornado warning. The case I'm showing here is there was a violent EF4 tornado in Northeast Texas last November, and I've outlined Red River County, Texas there in white. There was a tornado watch that came out at 1 p.m. that covers a good part of eastern Oklahoma and a large part of Texas. So at that point, we know within this region that there should be severe storms and a threat of tornadoes. But it wasn't until 5 hours later that an individual living in Red River County, Texas, received a tornado warning. So what's happening in between there? Well, in terms of the forecasters sitting at the desk, analyzing all the data they can, doing their best to communicate this threat, everything that led up to that watch issuance at 1 p.m. was informed by numerical weather prediction. And that's so key. All these model tools that we have allow forecasters to visualize the range of scenarios, the relative likelihood of different scenarios, and weigh how they're going to communicate those possibilities to the public. But when you get past the watch and closer to the warning time frame, everything in the forecast office quickly switches over to observation. It's all driven by satellite, by radar, by reports from the field. special balloon soundings. And in terms of numerical weather prediction, at best, for kind of a rapid update, you've got this single deterministic run of the high-res rapid refresh, the HRR. So what we wanted to do was, create a rapidly updating system that would better describe what's going on in between the watch and warning. So now flash forward to the era where we're starting to see what the War on Forecast system can do. And instead of only looking at satellite, radar, all observations that are taking place right before a warning, now forecasters have a numerical ensemble giving a variety of output that can help them visualize the different threats. And you see many of the examples here. In the upper left was just from this year in Oklahoma, where there was this dramatic ramp up of the significant tornado parameter right in an area where a localized tornado outbreak took place. And then WASP was showing that. You look at the lower left, that's from Phoenix, Arizona, a windstorm that produced pretty significant damage in the southern part of Phoenix last summer. And WASP provides a signal about 3 or 4 hours ahead of time of severe winds coming in off the mountains and developing down in the valley. Up the upper right, this is a machine learning based product that predicts the probability of severe winds, and that picked up on a storm that went through the DC area last May with a lot of wind reports. So you get the idea. There are various products, various ways that you can take an ensemble system and then visualize the scenarios that are taking place here. The lower right is a multi-hazard plot where we're showing all of the different hazards from a tropical cyclone on the same plot. You got wind, rain, and then some measure of low-level rotation in the storms for the tornado threat. And in addition to all this great ensemble information, forecasters can dig farther into the individual members if they choose. And those middle two plots there, you're looking at individual forecast members from WAFs and their simulated output there. So to kind of summarize what we've created, is this prototype War on Forecast system that's been having a lot of success experimentally, both in the test bed and in the real world. And if you look right-hand side there, I kind of point out what's special about the system. It really is, although it looks like numerical model guidance, it's really the first of its kind in terms of the rapid update cadence to it. So it's the first of its kind storm scale ensemble with data assimilation every 15 minutes, and then a relaunch of an entirely new suite of forecasts every 30 minutes. The output is projected out to 3 to 6 hours, and the ensemble itself consists of 36 members for the analysis, 18 members produce the forecast, all at 3-kilometer grid spacing, so pretty comparable in grid spacing to other systems that are used in operations. Because doing this in an ensemble sense is very labor intensive in terms of the computing power, we run it on a limited size domain. It's about the size of the 4 corner states, about 900 kilometers squared, and we can move that around the country to target severe weather and flash flood events. One of the exciting things since last year is that we've moved the system onto a cloud-based platform, so it's actually running on the Microsoft Azure cloud. And with that, we have a containerized system that you can plop down on any computer nodes and just run it. You don't have to compile. It's very easy to set up. So then in terms of the program overall, what we really try to emphasize with War on Forecasts is first of all, probabilistic forecasts of individual thunderstorms. We have recently an emphasis on machine learning development to calibrate the probabilities that come from such a system. And then really a lot of work with end users to visualize threats in very fast-paced severe weather environments. And so one of the questions that we get is how does this compare to that high-res rapid refresh model, the HRR? I think it is useful to take a look at those side by side. The HRR really is the state of the art for a single deterministic run in the severe weather realm. But the warm forecast system differs in some significant ways. We work closely with the Global Systems Laboratory, the creators of the HER and the creators of the new RRFS. And so there are some things that we share. For instance, the HER provides right now the initial and boundary conditions for WAFs. But then WAFs is doing everything at a greater pace and crunching a lot more data than you see in the HER. So first of all, it's a forecast ensemble. So any comparison between the two systems would be hard to make because you have 18 different forecasts in the WAFs that are then used to derive these probabilistic products. And then in terms of radar and satellite data, WAFs has a few more fields that we're assimilating. But the real key to it all is in the yellow box there in the lower right, that the cadence is so much quicker. WAFs is assimilating everything 4 times as frequently as the HER. And then the temporal output is at 5-minute resolution, so that forecasters see these kind of seamless movies of what the storms could potentially look like, because the design is meant for use closer to the warning scale. And by doing that, by putting output at 5-minute resolution, we generate a lot of images, and have had to think a whole lot about how to visualize this and do the post-processing very quickly, so those forecasts get out in a timely manner. So to kind of follow on that discussion of deterministic versus ensemble, I put together this slide to kind of talk about why we need an ensemble system for storm scale kinds of questions, because I do think that our science is really, really good at knowing the region where a severe weather outbreak is likely or possible at days in advance. You see the Storm Prediction Center outlooks out to 7 days will often have areas outlined. But when it comes to the warning details, the city and county level, thunderstorms are so chaotic in their behavior that if you run a deterministic solution, you're going to see convection that shows varying location, size, intensity, and motion. All these things kind of play off of one another and snowball into a very chaotic and situation that has a lot of uncertainty to it. So a way to attack that is with an ensemble system where you can derive probabilities, you can see multiple possible scenarios. And I've chosen this case from Florida earlier this year, where you had some unusually large hail occur on the eastern part of the peninsula. And I picked out just 3 members from WAFs, and you can see some of them paint a lot of storms capable of producing large hail in that zone of what I call the Treasure Coast there in Florida. Some of them have a few storms, and then there are a few members that have only 1 storm in that zone. But if we combine it all into the probabilistic products across the lower right, then we're able to describe the situation a little better. There's medium to even high likelihood of some storms producing large hail in that vicinity. And then the 90th percentile value from the ensemble predicts that you could get hail up to about golf ball size, and that was exactly what we saw reported at Melbourne, Florida that day. So this kind of speaks to that need for this kind of an analysis and going beyond the single deterministic runs. Okay, so this slide, I think if you're only going to take away one slide from today's talk, this is the one. This is what really captures the value that we've seen in these experimental WAFS runs on that watch to warning time frame, that we're really enabling communication of threats in that time frame, but also probabilistic communication of those threats. So what you'll see very frequently leading into an event is that at 3 or 6 hour lead time, such as over on the left here, there are many possible storm tracks. They're kind of varying probability, more on the scale of a watch box. And then as we get to say 1 to 3 hour lead time, some of the storms have already initiated. They're being assimilated by that rapid data assimilation system, and WAFs is starting to hone in on the tracks. So you have fewer tracks, they're a little bit more confident. You might be able to compose a mesoscale discussion to describe that. And then occasionally at the lower lead time, 30-minute swath or 60-minute swath, you see these highly confident little signals that are more on the scale of a severe thunderstorm or tornado warning. And so providing the tools to be able to describe all that tends to result in forecasters having more confidence to reach for some of these details earlier in time. So it might seem that we're doing pretty well here with some of the cases that I've shown you, and that's true. And so we've been in discussion with the National Weather Service on what a transition of this to operations would look like. We actually have a draft transition plan that we're still making some final tweaks and having some conversations, but we anticipate that that will go towards approval later in the year, and that we'll start working on milestones to get WAFs into operations probably around 2027, give or take. If you look at the EMCs, the modeling center's rainbow chart there on the right-hand side, WAFs is just in sort of a visionary way, seem to be around the time of the second implementation of the RFS, which would be about 2 years after RFS version 1. So we have some time, and that's good because there's going to be a lot of training needed and some infrastructure needed to develop to support warn-on forecasting operations. But so far, our conversations with the Weather Service have been very positive, and they're very supportive of this idea of working on this. And so I didn't want to go too far further without mentioning, if you're going to accomplish something like this, which was really a moonshot project, that's taken over a decade to come to this point, we certainly didn't do it alone, although there have been dozens of great scientists at NSSL and at CERO here in the building that have contributed over the years. We've had a ton of collaboration with our other in-house groups like the MRMS group, and then just within the Norman community in general, other universities, the National Weather Service, super supportive and giving us access to conversations with their forecasters in real time, which is just invaluable to a research group. And also modeling groups such as the UFS, trying to keep engaged in all these facets kind of helps inform the program. I think our group also, we really pride ourselves on our emphasis on user engagement. Since 2017, we've been running the WAFs that you see today in an experimental way in the spring forecasting experiment here at our test bed. We kept rolling through COVID with some virtual experiments, like the one you see pictured here. We brought together folks from the local forecast offices, but also the Storm Prediction Center and Weather Prediction Center, had them work some events that gave everyone something to do between the severe weather and flash flood threats. If you look at the image on the upper right, that's a map of all the 56 experimental runs that we performed in 2022. So you can see we do make an effort to get around to the corners of the country and give everyone an opportunity to get some repetition with the system. We hope that will continue to expand as we go with the transition plan moving forward. And even this year, we've already managed to get a couple of good severe weather events up in the Northern Rockies and Pacific Northwest. But it's not just forecasters. A couple of pictures on here where we've been invited to the aviation weather test bed. We know there's some excitement in that community now, starting to look at warn-on forecasts. And then we've begun conversations with emergency managers as well, and certainly hope to get to broadcast meteorologists in the near future. In fact, I've been invited to help design the master class for the National Weather Association meeting this August, or this September actually, and hopefully there'll be some broadcasters in that experience. So all this interaction, with our end users has resulted in tangible gains on the way that the system is visualized, and I've shown a few examples here. One of the more unique products is a paintball product you see looping in the middle. We have paintballs for various hazards or just for the storm locations in general. This in particular is a paintball plot of object velocity swaths, so that would kind of correspond to storm rotation. And this was a tornado outbreak, so you see the tornadoes popping up there as they occur. But it's a way to visualize all of the 18 members on a single plot. So these various different multicolored swaths are derived from the 18 members. Another unique kind of aspect of the web viewer is in the upper left, you can toggle between the observed radar at the initialization time versus what the members look like at that time. So you can get a sense of how well the members are initializing with the given thunderstorm. And then some other advantages you can read about on the slide here, some overlays for air traffic control, overlays for burn scars, and then starting to talk with some of our folks who are interested in fire weather forecasting to get more products for that aspect. Okay, so I wanted to spend a couple more slides on some of the tools that are in development, and then we'll look at some real world examples of how the system's been used. But another tool that forecasters have been pretty excited about is our machine learning based probability of the various weather hazards. This has developed over the last probably 4 or 5 years, really, but it's really become a mature kind of a product in the last 2 years with a lot of testing in the test bed as well. So what we're trying to do here is take advantage of the fact that in WAFs, we should, and at the scale that we're talking about, within a couple of hours of an event, we should have some confidence in where storms are likely to be or where they're likely to be moving. So we can kind of break away from that. What's typically done is to take a neighborhood around a point and derive a gridded probability. So here we instead define an event probability, being what is the chance that a given hazard is going to be reported over the next 30 minutes or next 60 minutes in the area where we think the storm is going. And so in that way, I think it really mimics the thought process of the National Weather Service forecaster who's trying to decide, do I issue a warning on this storm? The event space that we carve out for the machine learning probabilities is essentially where the algorithm has identified a storm and then where the different 18 members take that storm. So you can see we've done this for the individual hazards, and again, it's on a scale of 0 to 100%. What's the probability of receiving at least one severe report in that event space? And this, in general, has been one of the things that forecasters report they really like about the Warner forecast system, is that ability to identify what's the relative threat of the different hazards, because there are a lot of severe weather days where all of these hazards are possible, and it's not immediately obvious which hazard is going to dominate. So more on this particular product, there's a paper, and actually I should give credit to Dr. Montiflora and Dr. Corey Popman, who developed these machine learning based probabilities. And this is from their 2021 paper showing that they tested several different methods, but the one that really scored well was logistic regression. So it's the one that we've chosen to carry forward. And they've gone a step further. Dr. Flora in particular has gone a step further in developing these explainability graphics, which means that as a forecaster is using the system, they can click on an object that say it's forecasting 70% chance that a severe wind is going to happen, and they can see where that particular object falls on the distribution of the different predictors that were used in the training data set. And of course, there's over 100 predictors, so you wouldn't look at all of them, but I've been surprised myself at how useful it is to look at the top 4 or 5 predictors and see where the current object falls. It just really helps you kind of assess what that storm's character is or is likely to be. Of course, we're not advocating that you would use just this one product to issue a warning, but I think it does provide really good context when seen alongside some of the other products in WAFs. The example I could give across the top here from Southeast Iowa was from a tornado outbreak where the low-level rotation, or the 90th percentile of vertical vorticity, is showing several different swaths, and several of them are moderate or strong. But then I might be more inclined to prioritize the ones where the machine learning swath is showing, a 40 or 45% chance of a tornado occurring. In fact, that 45% swath is one of the strongest signals that I've seen from this product, and it happened to line up with right where an EF4 tornado tracked over southeast Iowa back in March. This stuff is still in development, and across the bottom there, it's kind of point to the fact that we're still exploring how to visualize it best. The looping image on the left, you see that the probabilities are decreasing over eastern Kansas as time goes forward. But maybe an even easier way to visualize that is by overlaying 1 hour swaths on top of each other, and you can see that kind of downgrade in the potential as time goes on. Okay, a couple other quick notes about the development work. I mentioned that we're running on the cloud. That's been true since 2022. And by the way, if anyone wants to go back and look at earlier cases, they're all on the viewer. Just go to waf.nestle.noaa.gov, and you can find our cloud-based viewer, and then also our older cases on a separate viewer to get to click around it and see what, get a feel for how to use Warrant Forecast. But this running on the cloud is great for us. It removes dependency on the sometimes less reliable in-house HPC. And again, being containerized, the CB WAFs, this cloud-based version, runs very quickly and easily wherever we need to run it. And it will automatically see the benefits of any upgrades that Microsoft does to their machines. And if we happen to fall behind, if initial conditions are late arriving early in the morning, then we can catch up to real time by requesting extra resources on the cloud, which is really nice. And just in general, we're helping explore this space of how to run in the cloud. And that's some of the knowledge that we'll be hoping to transfer with and talk with NCEP about as we start working on the transition. And again, it's actually really cheap to run a case on the cloud, only about $1,000 per day for a single domain. And so there are going to be other costs associated with storage, but it's really cheap to actually put it into action in real time. And so traditionally, we had been running just a single domain wherever the best event of the day was thought to be. But this year we've begun expanding, and so that Florida case I showed you earlier, you see there on the right, at the very same time that was going on, we had a domain over Texas, and you see some quotes on the left there. The Center Weather Service unit was using WAFs for their aviation forecasts in Texas at the same time that the science officer in Jacksonville was helping the Melbourne office with their hail event down there. So really exciting to see this, and we hope to do more of this going forward. Okay, so now let's talk about how are weather forecast offices actually using this in operations, and what are some of the key best practices, what are the key considerations that they need to be having in mind when they go to use WAFs. On the left-hand side here, one of the first points we make is that unlike other systems where you're using it for large-scale considerations many hours out, here what we're really doing is making individual forecasts of individual storms. And so it's the first step is to see how well WAFs has initialized a given storm and realize that there will be varying performance depending on how long that storm has been around for WAFs to get a good handle on it. And this is a great example from May of last year, where you see that the 3 primary tornadic storms on this day, WAFs is doing great because those are large storms. They're long tracks, so they've been around for a while, many assimilation cycles. WAFs really has a good handle on those. But there's other parts of the domain where you see misses, you see false alarms, and in some cases the false alarms are robbing energy that is causing other storms to die when they shouldn't, like the one coming out of the Texas Panhandle. So really a lot to consider, and we, coach forecasters to consider individual storms when they go and look at the data. And that point can be kind of driven home by the chart on the right-hand side here, which speaks to that predictive capability that increases the longer a storm has been around. So what we're plotting here is the performance in terms of predicting where a storm will be at the time that it will be there. And that performance gets better if you've had some assimilation cycles on that storm before you run the forecast. Or if you've had 30 minutes worth, that's even better. 60 minutes worth, that's fantastic. A probability of detection of 80 or 90% that doesn't go down too quickly over time. So one of the key points for forecasters in all this is that you can't give up on WAFs. If it's not doing well initially, it can really recover because it's in the game. It's constantly analyzing new information coming in, and it can really catch up. And it's perfect transition into the next slide, actually, because a great example here. The example across the top is probably one of the most successful real-world cases that we've ever had with WAFs. This was a derecho that occurred in eastern South Dakota on May 12th of last year. But as you can see from the 18 UTC forecast on the left-hand side, it initially was not a very good forecast. The WAFs information is in the colored image, and the real-world storms are in those black splotches that are moving out ahead. So the WAFs forecast at 18 UTC was well behind, and it wasn't very emphatic. The probabilities aren't very high. It's just too slow. But once the storms started to initiate in Nebraska, WAFs got those assimilated, got a better handle on it. And at 19 UTC, you can see much better. It's not falling too far behind, has kind of the right shape of the storms. And then by 20 UTC, it's near perfection. Really good timing. You can see the winds are plotted there. The local storm reports are those blue boxes as we move forward in time. And we always say that it's a good thing if the observed storms in the black look like they're laying down the probabilistic swath from WAFs. So in real time, in this case, we were chatting with forecasters in Nebraska and South Dakota. We have a Google chat room that's been set up for a few years, began in southern region of the Weather Service and then expanded to the full US last year. And our interactions, we were able to give them the confidence in the output they're seeing to make some real world decisions, like using wireless emergency alert tags on the severe thunderstorm warnings because the winds are going to be that extreme. Or the Storm Prediction Center putting in their mesoscale discussion the likelihood of 100-mile-an-hour winds based on some of the consistency in WAFs. And so we're starting to get to the point where there's so many examples of this kind of groundbreaking accuracy that it's hard to choose which to show because they all seem important. But I've picked a couple of here. You got the Nashville tornado from 2020. Where within a couple of hours ahead of that event, WAFs is showing a high probability of rotating storms coming into the city of Nashville in 2 to 3 hour lead time. So there's potential to take some real action there, whether it's not issuing a polygon warning 2 or 3 hours ahead of time, but some way of getting more effective lead time by communicating the threat. And then the Utah example here, this rainfall of about 3 to 4 inches actually derailed a train in that location, and WAFs had a good 3 hours lead time on pinpointing exactly where that rain was going to occur on a day where there really wasn't a lot of heavy rain in the whole domain. So there obviously was something that WAFs was picking up on the environment there, allowing it to do a good job. And we kind of see this in a lot of cases. And just one more to kind of drive home the point that it's not just the big scale derechos, the tropical cyclones that WAFs seems to do well. It's often these smaller scale signals that can be really useful. This is an example out of northeast New Mexico that the Albuquerque office actually brought to our attention when it was happening, because they had noticed that if you look at the lower right, there's a very strong signal, very strong likelihood of severe winds in the model. But if you go look at the individual storms, they're actually falling apart in the model forecast in that location. So what this was picking up on was the collapse of a thunderstorm in a relatively dry environment. And you see kind of a difluent wind pattern that shows up in the lower left-hand image. And there aren't many observations out there, but the one that we did have was the 50-mile-per-hour gusts measured kind of right at the edge of that model signal. And again, forecasters were able to pick up on that. Okay, but I always do want to include, one slide at least to remind ourselves that while all of this is great and it's we're unlocking things that we haven't been able to see before in operations, it doesn't do everything well, and I wouldn't expect that any system would do everything well. But there are some common failure modes. Most of them dealing with the environment. If the environment isn't analyzed properly, well, then you're not going to model the right character of the storms. And so this is an example here of where WAFS has the dry line in western Kansas a little too far east, and so from radar it assimilated the storms where they should be, but in the model it's west of the dry line in the dry air. They immediately died in the model, whereas in the real world these went on to be very impactful, kind of long-lived storms. There are other storms such as shown in Georgia in the upper right. This was just earlier this year, where they were so narrow or so small that it's just hard to resolve something like that at 3-kilometer grid spacing, even though they were severe storms. And then we don't have a really good sample size yet of the sort of wintertime, early spring, low instability, high shear cases. But we saw a pretty big failure of the 3-kilometer WAFS for the December case, the Mayfield, Kentucky case a couple of years ago, where WAFS just wasn't able to sustain those storms. However, the March 31st case this year, which had a little more instability, it did really well. And when we run higher resolution models on the Mayfield case, they also do well in a WAFS setting. So that may just be a resolution problem. So what have forecasters been able to do with all this? One of the most common uses is to produce what we're kind of terming as a watch to warning graphic, or the watch comes out from the Storm Prediction Center, so it's at some scale, and then the local offices are able to say, well, over the next couple of hours, this is where we're really focused. And you see here the example showing Kingfisher County in Oklahoma being outlined, that eventually that's the county that comes under a tornado warning. That's where we have the tornado within a couple of hours. So the ability to be a little more specific spatially, and then some of the language too. And occasionally you'll see, in this area expect a supercell, whereas in the past we would have been saying supercells are possible. Now it's more like, well, we know which supercell, it's out there and WAFS is tracking it. So just these subtle differences that lead to a little more confidence in the language that's being used. And this, I'm sure, looks like a crazy slide with too much on it, but I didn't want to, I can't show all these examples and give them all the proper time, but I just wanted to point out that there are a number of ways that this information has been used in the real world, such as the lower left. That's the Masters Golf Tournament from 2022. And the office in Columbia, South Carolina, was able to give a heads up to emergency managers based on some of the lightning probabilities out of WAFS. Occasionally, it's simply a chat message to partners, like the Chicago office did for a rotating storm in the upper left there. And on rare occasion, we've seen a literal kind of a warn on forecast concept where forecasters drawing up a flash flood warning, and they see that just downstream there's this heavy signal out of WAFS, and so they go ahead and make that warning a little bit larger into areas that haven't even rained yet. And so again, too much on here to read, but this is for, if you want to download the presentation later. in general, we've heard a lot of positive feedback from the users that all kind of boils down to the fact that WAFS is giving forecasters the confidence to communicate specific scenarios at greater lead time. And then my favorite quote, in more of a lighthearted way in the lower right, out of the Albuquerque office: once you start using WAFS, the days where you don't have the domain of your area, you're kind of mad. Okay, I know we're getting a little late on time, but I think I have time to get through just this last little bit here. I didn't want to give a UFS webinar without tying WAFS to the UFS and talking about our work there. So for one, we have a close relationship with the Global Systems Lab, the developers of the RFS, and to now the emphasis within UFS has been on the RFS. And I think that emphasis on WAFS will be coming soon as we get the transition plan signed into action and begin working on those milestones together. But a couple of the ways that we have been contributing thus far, NSSL has a microphysics package put together by Ted Mansell, and that's now available in the Common Collaborative Physics Package, CCPP. If you look at the notes at the bottom of the screen there, that package is a fully double moment microphysics scheme. He has a 3-moment scheme that's soon going to arrive. And in particular, the Nestle microphysics is the only one that we know of that has a hail species that's intended as the true hail. So it's only initiated from large wet growth graupel. We also have some folks who participate on UFS teams, such as Larissa Reams, doing some code management for the short range weather app. And importantly, over the last few years, our group has performed quite a lot of work to develop and vet the use of the FV3 core for this rapid data assimilation kind of modeling that we do in WAFS. So let's talk about that for a couple of slides, and then I'll wrap up here. So I'm just going to try to summarize what we've found in our workings with the FV3 core. And we went into it with probably 2 or 3 key questions. Again, we had developed a system that works really well using the WRF model. So we needed to have some performance that at least got in the neighborhood of what we were seeing out of the WRF. And first of all, could FV3 represent the structure of these convective storms on these local scales that we're interested in? And this is an example from a May case in 2021, again in Oklahoma. Apologize for so many Oklahoma examples here, but this image on the left-hand side shows you the observed radar at a particular time. And then you got the traditional, the WRF WAFS. We've picked out several members there to show the simulated reflexivity, and then the FV3 version of WAFS on the far right-hand side. Again, a collection of different members. And there are some important differences worth noting here. The most, and probably the first one that occurs to me, is the nature of the individual updrafts in the FV3 are a lot more circular. They don't look like they're communicating kind of between each other. It looks more like a collection of cells in kind of a weak shear environment rather than a combined cold pool that's sort of forward propagating, where you get this linear kinds of updrafts on the leading edge, which is more like what you do see in the WRF-based WAFS. And in addition to that, the stratiform region is much better represented in the WRF-based system. But the longer you stare at this, there's some other differences that are maybe even a bigger issue with the FV3 version. There's a lot more storms that have initiated in Southwest Oklahoma, which shouldn't be there for the image on the left-hand side. And then there are other cells in the Texas Panhandle. That once you get these spurious storms introduced, it's really hard to remove them, even with the data assimilation. So secondly, we were looking at, could the FV3 in WAFS handle this rapid data assimilation cycling and on a targeted domain. A model that's performing really well at the global scale, can it do this small regional scale, to our satisfaction? And so this is the same case, kind of looking around the same time. And I've got some different verification data on the left-hand side there, where you can see there's a distinct kind of a southeastward movement, and the severity of the reports is particularly concentrated right where that bookend vortex is on the developing MCS, kind of east of Oklahoma City. Oklahoma City is the white dot there. And so on the right-hand side, you're going to see one column that's got the WRF WAFs, the other column is FE3 WAFs for the mid-level updraft helicity swaths, and then an accumulation of reflectivity over a 3-hour period. And in the WRF WAFs, we see that representation of the bookend vortex area, a heavier concentration of probabilities for updraft rotation there, some indication of more intense reflectivity. Whereas in the FE3 version, the reflectivity is more kind of uniform throughout. There's not really an indication of that concentrated area east of Oklahoma City. And in particular, in the helicity swath, it's very pockmarked, and you don't see a sense that things are being maintained and moving southeastward. It's almost like just the individual updrafts are going up and then coming down and propagating toward the southeast, but not in a real coherent way, at least the way you visualize it here. And so finally, number 3, this was actually a really high impact case, and one that was kind of ideal from the legacy WAF system, where it was a flash flood event prior to the formation of what I was just showing you on the north side of Oklahoma City, where more than 5 inches of rain fell. And the WAF signal was so compelling there, with probabilities of greater than 5 inches, that the Norman Forecast Office used that signal to issue a flash flood warning for Logan County, again, in areas where it hadn't even started to rain yet. And you don't see that compelling signal in the FE3 version of the model, where the max rainfall on the 90th percentile product is actually 2 inches, but it's actually associated with a storm down by Lubbock instead of Oklahoma City. So really just 1 to 2 inches of rainfall in that product from the FE3 version. So that would not have supported, that real world use that we saw from the Norman office. And so kind of summarizing all that, you look at points number 1 and 2 there, just summarize the slides I've shown you. And then after working on this and doing considerable tuning of the system, our conclusion as of really late last year was that the FE3 just simply wouldn't work for what we're trying to accomplish in the War-on Forecast system. So the intention here is to offer the WRF-based WAFs for the first operational version. And then we're exploring the addition of a second dynamic core, potentially into the UFS, the model for prediction across scales, or MPAS. And we're doing the same kind of vetting on it that we started to do, for the FE3, to see if it gives us more promising results for like a second generation version of WAFs. So this is actually my last slide. The future includes working on the MPAS to see if that is a viable solution. We're already in development on a 1 kilometer grid spacing version of WAFs. And then again, data assimilation of new data sets at this rapid pace. There's lots we can do potentially with phased array data, uncrewed aerial systems. And the great thing about being at NSSL is you have folks who actually go out and gather these data sets in real time and are housed right here alongside the modelers. So there's a really quick way to talk back and forth with each other. And then finally, I think something that is receiving a lot more of its due attention throughout the weather enterprise is this idea of social vulnerability and producing more equitable lead time kinds of approaches in places that need more lead time, just because they have fewer resources or more complicated sheltering options. And so we're looking to work very soon on pairing WAFs with the CDC's Social Vulnerability Index and put together some good work working with our partners in operations. So Kind of a big statement to end the talk here. There's never been an ensemble like this, but what I mean, like there really hasn't been this rapidly updating ensemble guidance at the city and county level in between the watch and warning until now. And so what we're seeing from that is pretty exciting. We're learning new things every time that we run the model. But that also means that the transition will require a lot of us. We're gonna have to communicate really well with our weather service partners to build the expertise and the data infrastructure for getting this into operations. But we look forward to doing that. So that I will stop.
Thank you so much, Patrick. We have a bunch of questions that have been typed into the Q&A document. I'm so excited to see, the amount of activity on this. So give me just 1 second to pull up my screen. All right, can y'all see it? Maybe I'll make it a little bit bigger. Great, Patrick, whenever you're ready to go through these.
Okay, just grab a beverage chill real quick. All right. Why that particular ensemble size? Yeah, we get that question a lot, and I think it's partly related to the limits we had with the in-house computing that we were using at the time that WAFS was developed. There have been studies even in the test bed here in the building about using fewer members to save on compute resources, and that those have shown some promise, at least for larger scale thinking. But that's actually built into the transition plan to revisit this now that we're in a cloud-based environment, now that we know a lot more than we did 6 or 7 years ago. That is something that we'll be looking to refine. So number 2 there, given that there wasn't a lot of heavy rain in the region, in the Utah case, what prompted the decision to make a WAFS run? Oh yes, yeah, that's a very good perception there. That was a retrospective run. So the Salt Lake City office just gave us a heads up that this had occurred, and so we went and ran to see what WAFS would have shown. So yeah, I should have made that distinction clear. We do that quite a few times a year. And so I think the weather offices are pretty good about, coming to us and requesting those things. So that's part of our process. Are the errors correlated to the complexity of terrain in any way? So to what? Okay. Wow, that would be a good question if Lou were on here. The only way I really know to answer that is that I know our chief scientist, Lou Wicker, has told me that in the time before storms have initiated, the model will have a much better chance of getting the location right if there is some terrain influence. And there's a particular case that I'm really familiar with from the DC area in 2020, where there was flash flooding at Leesburg, Virginia, and WAFS did a perfect forecast for that storm before it had even initiated. But there is some terrain just to the west of town that initiation took place. So that certainly, I think, gives the model a leg up on getting things right. Are others able to run this system if they want to? Yeah, we were just talking about this at one of our meetings this week. At this time, no. I think because of the complexity of running it, but we are very open to collaborating with groups that would like to explore the space. So we would just ask that you write to me, write to one of us, and we'll try to connect you with the research scientists who can work with you, on your ideas. I do imagine that in the future we'll get there. We'll get to a point where it's more open source, particularly when it becomes part of the UFS, hopefully, in the near future. Lightning forecast for the PGA Tour. Do we have explicit lightning forecasts? They are explicit in the sense of flash density. So what we're estimating is the number of flashes, and so that would include both intra-cloud and cloud to ground from a storm. And that's about the extent of my knowledge of that particular algorithm. But yeah, it gives output the probability of, say, 10 flashes in a 5-minute period, or the probability of 25 flashes. I think those are two of the products that we do. Have you worked at all with the Jedi? Oh yeah, another great question. These are really good. That will need to be part of the second generation of WAFs. So we actually haven't taken that step yet in the current version of WAFs. But it certainly is something we talk about all the time, is we know we need to do that. And so, yeah. Do you want to say that?
Yeah. Yeah, so we've actually, as Patrick mentioned, we've been interested in interacting with the Jedi team really since we first heard about all the cool stuff that they were going to do. But as to date, the type of data assimilation that's required for the one-on forecast system is not available yet within Jedi. And so as soon as it is, or they need some testing for that with a system like we have, we'd be happy to be a part of that.
Okay, the flash flood case, it looked like predicted high rainfall from work WAFs is outside of the region where high rainfall occurred. I think probably referring to the case where we compare against the FP3 WAFs. Now, if I remember correctly, what you might be referring to is that what I was showing you was kind of midway through the event. So the areas back to the west of that, the western half of that warning polygon had already received rain. And so the key use of the WAFs was to look downstream, and the forecasters were saying to themselves, okay, we're drawing a warning for this rain that's falling, but is it likely to be just as bad, 10 or 20 kilometers east of here? And that's what WAFs was showing. So it's so if that makes sense. What element of the work core makes it so much more suitable / accurate, at least at these scales? And I have a note here from our chief scientist, Lou Wicker. The WRF model was designed to do convection from the beginning. I think that's true. You look at I think a lot of the emphasis early on in FV3 has been, to revamp the global model, the GFS, and certainly they've been successful in doing that. Whereas the WRF is designed more by folks who spent their careers studying convection, so with very, focused intent on modeling convection. And so, and there are some other issues such as the FE3 being a global hydrostatic model at the beginning. The fundamental, design is just wasn't towards convection from the beginning of that development. And then number 9, finally, would it be possible to modularize WAFs to be plugged into any dynamical core and data assimilation module? I'm not particularly a modeler, so I might not be the best to answer that. I think it makes sense to me that it probably could be done. I've not heard that suggestion before, but that's one we'll.
Yeah, I think there would be sensitivities depending on the grid the type of grid and other things like that. So there would always be, I think, some work involved, but I mean, that's essentially what we've done and what we're doing with respect to working with a variety of dynamical cores.
Yeah, I think technically it could be done, but it might be tricky. Okay, well, Shira, I'm sorry we've gone over a little bit, but hopefully that was worthwhile.
Yeah, not a problem at all. It was a robust discussion, so I'm glad. Thank you so much, Patrick. Thank you so much, Pam. Thank you, everybody who attended. Please tune in to our next webinar, which is going to be July 13th, and we will see you then.